Hi, everyone. So in this lecture, the objective is to understand the meaning of relativistic energy, and in particular, to explore the connection between mass and energy. I just want to do a quick recap of what we did last time. The upshot of last lecture was that because we're working on a new relativistic stage with a different interconnectedness between space and time, all the dynamic quantities must get an update as well. We saw that the old definitions the old definition of momentum, just mass times velocity, doesn't work. That definition makes the momentum conservation not Lorentz invariant, so it doesn't work. And through an argument about collision, we came to a conclusion. Well, first of all, momentum must be updated to this definition, and second, it drags along with it conservation of this other quantity, which we interpreted as energy. Now, in classical physics, we also believe in energy conservation. When you have a collision, if there are no external forces, if it's an isolated system, momentum can be shown to be conserved. And we also believe in energy conservation. There has never been an experimental evidence that the total energy is not conserved. If it's an elastic collision, the energy is stored in the form of kinetic energy before and after. If it's an inelastic collision, some of the kinetic energy is transferred to other forms. It could be internal potential energy, it could be thermal energy, but the total energies are always conserved. But this idea was a separate idea. When we step onto the relativistic stage, conservation of momentum drags along with it conservation of energy. It necessitates the conservation of energy. So these two quantities are now interdependent, just as the space and time is interdependent. Now, I dropped this idea that the interdependence of these quantities is a consequence of space and time interdependence, but I didn't explain why. This was just kind of a dropped an idea. If you want to explore that more, you can watch the optional video of lecture 11, where I discuss 4 vectors and so on. In any case, the objective of today is to explore this guy. Let me write this out explicitly in terms of velocities. Now, I want to emphasize that this is the total energy. So if you have an object, it's moving, it's the total energy of that object. And I can write it like this. Now, as velocity goes to 0, this approaches mc squared. That's an interesting expression. And if velocity is not 0, well, what I can do is I can Taylor expand this gamma factor. Now, some of you are getting cold chills when you hear the word Taylor expansion. That's not good. It means that there is some kind of a fear that was instilled in you by the calculus class, and I can assure you a lot of those calculus instructors are also afraid of you, just like you're afraid of them. Taylor expansion is just an approximation. So this denominator, the gamma factor, or the whole gamma factor, it starts out at 1 and it blows up at u equals c. And what we want is we want to include this dependence at small velocities. So that's why it's called expansion. We expand the dependence at small velocities. You can try. So when all the dust settles at small velocities, the expression is, well, mc squared times 1 plus 1/2 u squared over c squared, plus their higher order terms like u to the 4th, u to the 8th. And so we see that E total now it becomes an approximation, right? So E total is mc squared plus 1/2 mu squared plus that. And when we stare at this, we recognize that, oh, this is just conventional kinetic energy. So evidently, so all these terms, they're kinetic energy. But this little guy is not, all these terms are kinetic energy, they're part of the kinetic energy. The kinetic energy is no longer 1/2 mu squared, it's all these terms right here. They contribute, that's things that depend on the velocity. That part of energy is the kinetic energy, but this little guy does not depend on the velocity. So even if velocity is 0, an object still has energy. Now you might say, well, I kind of knew that, right? So I have an object resting on a table. It probably has energy because it's made up of molecules. They're whizzing about, they have kinetic energy, they're interacting, they have interaction potential energy. That's true. But think about this. This tells you the total internal energy content without you having to calculate that. This doesn't know anything about the properties of the particles that make up an object. It just says that, well, the total energy of the object is related to its mass. So this thing, because it doesn't depend on the velocity, this is called a rest energy. It's the energy that an object has when it's at rest. When it's not at rest, it has additional energy, that's kinetic energy. And because it's proportional to the mass, it's also called mass energy. This is a very interesting expression. It suggests that inertia of an object, which is what mass is equivalent to an energy of the object. And it allows you to compute the total internal energy of the object from just knowing its mass. You don't have to think about the chemistry of the interacting particles or the details of what makes up that internal energy. So we will be digesting the meaning of this. We'll try to wrap our mind around what exactly does E equals mc squared really mean. So I should say E total minus mc squared equals kinetic energy. So everything else is the kinetic energy, and the mc squared part is called the rest energy of an object. And in the rest of the lecture, we will digest the meaning of this rest energy. Okay, so see you in the next part.